one of the organizers. You know that self-eating conflicts will happen. Yeah, it's something. Remember how long is the top? 15 minutes. Right. I have a watch.
Michal Kapustka, title is EPW.
Thank you. So let me start by thanking the organizer for the invitation. It's an honor for me to be here. Professor Rozak is not here. Let me start the talk. So I would like to present a construction of a new family of hypercolor manifolds. So we're going to work with Michal Kapustka and Michal. So I will profit from the fact that we already had hypercolor manifolds discussed a few times during this conference. So I'll not say much things about them. I'll just recall some facts. So maybe just for those who don't remember, the definition of hypercolor: X is hypercolor if it is smooth. So I will use the definition also with projected, simply connected. With trivial canonical class and the H20 generated by one symplectic form. So omega is a indegenerate holomorphism. So this is slightly different, but of course equivalent to the one that we have heard already. And the main point is that it's very hard to construct such examples. Hard to construct in dimension higher than 2. So for dimension 2, hypercolor manifolds are just K3 surfaces. But for higher dimensions, so it was long unknown whether there are any examples. Then there are 4 types known for deformation types. There are deformations of either Hilbert squares of K3 surfaces. So I will denote Hilbert schemes of endpoints on K3 surfaces. I will denote them like this. We have also generalized Kummer. So in the Hilbert scheme of points on an abelian surface, we just take those sets of points which sum up to 0. And there are 2 sporadic families of dimension 6 and 10 due to ODAD. 6 and 10. So when I say we construct a new family, it doesn't mean that we go outside any of these 4 classes, unfortunately. It deals with another problem. So the problem that we deal with, or the difficulty that appears here, is that even for this case, so in fact our family will be of this type. So not of this one, but of this one. So the point is that whenever we have a hypercolor manifold which is a Hilbert scheme of a K3 surface, and it has some polarization, then the moduli space of polarized hypercolor manifolds with this polarization is 20-dimensional, whereas this family of K3 to the n is at most 19-dimensional. That's why the general element in the moduli of polarized hypercolor, for instance of K3 type, K3 to the n type, is not a Hilbert scheme. So the problem that we deal with is the problem of construction. So problem is construct families which are called complete families. Complete families of hypercolor manifolds. By this I mean that the map to the moduli space, so there is a coarse moduli space of polarized hypercolor manifolds, and the map from this family to this moduli space should be onto an open subset of the moduli space. Okay, so we described components of moduli space of polarized hypercolor manifolds, and there are only, in this case, there are only 5 known constructions so far. So maybe I list that here. So 5 known families. So I will describe just describing elements in these families. So the first one is the Fano of lines, Fano variety. So it's not a Fano variety, but is the Fano variety of lines on a cubic fourfold. So this is due to William Donaghy. It's a very old example, very classical. The next one is also related to the cubic, is the variety of sum of powers of a cubic in 6 variables, so f cubic in 6 variables, which is also a sum of cubic fourfold. We parameterize the space of the compositions of this cubic polynomial into 10 cubes of linear polynomials. So this is the variety of sum of powers, and it gives also a hypercolor. This is due to EDF from the start. So these are parameterized by cubics, and cubics up to equivalence gives a 20-dimensional family. So these are 20-dimensional families of hypercolor manifolds. Then there is the EPW, double EPW sexty. So this is ODND, and I will say a bit more about this construction later, since you see there is this EPW here and EPW here, which they are related. So EPW comes from Eisenbart, Popescu, and Walter. So there are some special techniques that I will introduce, and they are already introduced in Sasha's talk. So the next one is subsets of the Grassmannian G610, which are parameterizing 6 spaces, isotropic with respect to a free form. To a chosen free form. So this is V3. Finally, there is a fifth one, a recent one. So yes, this is the Barbasan. And the last one known is also related to the cubic fourfold. Is not quite. It's related to the moduli of twisted cubics. So the Hilbert scheme of twisted cubics. So the Hilbert scheme of twisted cubics in the cubic fourfold.
Do you remember the degree for this case? I mean, the top power of the polarization.
I don't think that they are all known, but all known. This one also. Last one. So the degrees here it's 6. Here it's 6. Here it's 2. I mean the Bogomolov form. 6, 2 here. This I don't remember.
22.
22. Okay. And this one? This is split and not yes, maybe. So it's another component of the same moduli. Yes, and here I don't know.
Here is 4. But are not the equivalent? And then the third and the last with 2.
So this is an 8-fold.
Oh, it's not 20.
These are 4 folds, and this is an 8-fold. Yeah, so the aim of this talk is to introduce a sixth fraction of the 6-fold, the most 6-fold of the picture, which is related to the EPW set. So the 6th one will be double EPW cubes. So before I say how to construct an EPW cube and the double cover of it, let me pass to recalling the construction of O'Reilly. So about EPW sets. So what are EPW sextics? So we start with a 6-dimensional vector space. And then on wedge 3 of this space, we have a form, even if you once we fix a volume form on wedge 3, 6, we have a form here that takes alpha beta to the volume of the wedge product. And then there is also an action of this onto the wedge 3, so we will work in the wedge 3 of this space, where we have this symplectic form. And this action on the projectivization has 4 orbits. So let me write the orbits, or orbit closures. So the orbit closures are just the biggest orbit is an open subset of this, so the closure is the whole space. Inside we have a quartic. So this is 19-dimensional. This is a quartic of codimension 1. Inside of it we have a 14-dimensional locus. And in the last one is the Grassmannian. This is the only closed orbit. Grassmannian G36, which parameterizes the composable difference. Yes, and already the EPW sectors are related to this orbit. So let me write what is this omega 14 in terms of forms. It's just the space of forms which decompose as a product of the one form and the two form. And the A is in P6 and the A is in wedge 2. Yes, so each such form is annihilated by an A, and in general, so whenever we are not on the Grassmannian, we have a map to P5, which takes this, such a form A beta to A here. This is the unique form whose wedge product with this form is 0. And we have another, in fact, projection to the dual P5. So this is the projectivization of D6. And in the dual space, we have it goes to A wedge beta, which is also well defined. So we have two projections. We'll consider this one. So consider a fiber of such a projection. The closure of the fiber of such a projection is just the space of forms which are of the form A wedge beta. There's some beta in wedge 2. D6. So this gives us a fibration of the complement of the Grassmannian in this orbit. And so now we have this symplectic form and this fibration. So we observe that these fibers here are Lagrangian with respect to this form. Means that if I restrict this form to this space of forms, then it's 0. Yes? So we see that any two forms from this space, their wedge product is 0 because they all have A. So this means that eta restricted to Fa is 0. Fa is half of the dimension of the space. So the whole space is 20-dimensional, the wedge 3 D6 is of dimension 20. And Fa is of dimension 10 because it's isomorphic to wedge 2 B5. So it's half dimensional and symmetric 0, so Fa is Lagrangian. The definition for each A. So we have like a Lagrangian family of Lagrangian spaces. And then to construct the EPW sextic, we need to choose one more Lagrangian, the general one. So take A Lagrangian inside wedge 3 B6, and now we can consider the Lagrangian degeneracy locus corresponding to this family. So we just consider inside P5 the parameter space of our family. So S K A is the subset of P5 consisting of those classes alpha in P6 such that A is good. That Fa intersected with the chosen Lagrangian space has dimension bigger than or equal to k. So S0, of course, is the whole space. And now S1 is in general a hypersurface, a sextic hypersurface. Which is called an EPW sextic. So whenever it's a hypersurface, it's called an EPW sextic. And then in general, so for A general, this degeneracy locus, it's a Lagrangian degeneracy locus. So this S1A is singular only in S2A. And S2A is a surface in general. So the EPW sextic is a fourfold, which is singular along the surface, and this surface is smooth. So in particular, S3 of A is empty in general. So what O'Grady proved is that whenever we have A general enough, then let's see again. If A is general, then there exists a double cover of S of the EPW sextic, 2-to-1 cover, branched only in the singular locus. In the surface, and such that YA is a hypercurve. So now how do we generalize this? So the idea of our construction is to consider another family, natural family of Lagrangian spaces on the same picture. So far we have these fibers, but on the picture we have also the Grassmannian. And as it was already told in Laurent Manivel's talk, the tangents to the Grassmannian G36 are also Lagrangian with respect to this form. So we have a family parameterized by the Grassmannian G36 now. So for each U in G36, we consider the projective tangent of the Grassmannian in the point U, which in terms of linear algebra is just the projectivization of H2U to H6. So these are forms which are a product of a 2 form from U and a 1 form, a U1 form in Lagrangian. Just so again we can check it. If we have a 2 form times something, and so a sum of such objects, which are 2 forms and something, and we multiply them, then these 2 forms get multiplied. And this is a 3-dimensional space. We get 4 forms on a 3-dimensional space, they must be 0. So these are also Lagrangians. And we have a family of Lagrangians parameterized by G36. So by a choice of A, To the same A, we can associate another degeneracy locus, Lagrangian degeneracy locus, this time in G36. This is the locus, so I define dka in the same way, is the set of mu inside G36, such that this space wedge to U G6 intersected with A has dimension at least K. So here the situation is slightly more complicated. We are at higher dimensions. But the codimensions of Lagrangian degeneracy loci, so any time we have something like this, it's called the Lagrangian degeneracy locus, and it was studied by Dragacz and Ratajski. So the codimensions of Lagrangian degeneracy loci in general are known. So for A general, and in fact we can be more explicit here. But yes, I will be more explicit later. We have the 1A is just a hypersurface in G36. So it's in fact G36 intersected with some special quartic. Special quartic. And again, it's singular only in the next locus, which is D2A, which is dimension 3 now. So it's a sixfold. The sixfold, which is singular only in the next locus, D3A, which is now codimension 3 in this sixfold. It's a threefold. And D4A should be codimension 4 in this threefold, so it's empty in general. That's of course something that we need to prove that this happens. This is the expected codimension for the degeneracy locus. So now our theorem is that the sixfold admits a W cover which is branched along the threefold, the singular threefold. So I just take the theorem of O'Grady. There is S1A, and then D2A, around the threefold D3A. Maybe denote this way. But blue I is a high equivalent sixfold. So this is the construction. This is the.
So I'm sorry. In the previous version of this theorem and in this version, what would happen if A is not Lagrangian? So it will there will be no covering. There will be no the covering point.
No, even this.
It will not be.
The degeneracy loci wouldn't have the right codimension. So this wouldn't be a surface anymore. The fact that the codimension here is 3 is only because it's Lagrangian. Yes, so this is our result, and now I'd like to show a sketch of the proof before I pass to some other nice properties. So there are two steps, two main parts. So sketch it first. So step 1 proof construct the W cover. And then prove that it's hypercover. So the construction part as follows. It's very technical, of course, but we can see it on the step 1. You can see it on the following diagram. So the space of the Grassmannian, which parameterizes all Lagrangian subspaces in switch 3d6 with respect to this form eta. So this is a Lagrangian Grassmannian. We will note it like this. And our family, which takes U in G36 to T U in LG just a badic of G36 inside this big Grassmannian. So maybe I need more space. So we have this embedding. Maybe I'll just erase here. We have this embedding of G36 inside the Lagrangian Grassmannian. So we have G36, which is embedded into the Lagrangian Grassmannian from H3D6. Then here, inside of this, we have the degeneracy locus, the second one, which is embedded into some universal degeneracy, second degeneracy locus in this Lagrangian Grassmannian, which is defined in the same way, but for all Lagrangian Grassmannians parameterized, for all Lagrangian spaces parameterized by this, which is all Lagrangian spaces. But here, this universal Grassmannian has natural resolution. Which is contained in the product with G. So this in fact is exactly the set of pairs of spaces, Lagrangian space and two space in A, right, here, such that L is contained, K is contained in L. So whenever K is yes, but K is in A. So if K is in L, then K. So this is equivalent to say that K is in L intersected with A. Yes, so this projects down by the projection to the Lagrangian Grassmannian to the second degeneracy locus, because L must intersect A with something of dimension 2. But sometimes L intersect A in bigger dimension. And then we have a fiber, which is just the Grassmannian of this intersection space, of two spaces in this intersection space. So this is a resolution of singularities, because this has a map to the Grassmannian G2A with fiber which is smooth. It's just a Lagrangian Grassmannian. So then this thing, which is quite classical, via this resolution, this our D2A embedded there also lead to a D2A tilde here. So we have this map. So what is nice is that there is a theory of Lagrange Grassmannians, and we can see the exceptional divisor of this resolution. We can compute it in terms of the class hyperplane class here and the hyperplane class here. So it's in fact H minus 2R. So what we see now, that the exceptional divisor here of this resolution, we have an exceptional divisor which goes down to D3A inside here. It's just the restriction, the pullback of this one via this map. But we want to construct a double cover which is branched only in this divisor. Now this is a smooth variety. A technical result is to prove that this is a smooth variety. Then, if it's smooth, then there is this exceptional divisor. So, if we have a double cover of this one, we are expected to lift it to the resolution. It's a double cover branched along the divisor, the exceptional divisor E. So, this is the pullback of this. So, it's enough to see what is the pullback of H via this map, and so we get like 4H small minus 2R, where H is the hyperplane class of the Grassmannian. So this is just computation. So we get an even divisor, we know its class, and we can compute. So for all of these, this implies that D to A tilde admits a double cover. Branched in E, the exceptional divisor. So we have our D to A tilde here. We have this YA tilde covering it. We can even compute the canonical class of all these things. And we have this map to dA here. So this is 2 to 1, and this is just a resolution of singularity. So this is given by some divisor, this composed map, and then the multiple of this divisor, or factorization of this map, must be through a contraction here, and the one cover here. So we have YA. YA will be branched only in D3A, which is what is the image of E under this map. So we have a 2 to 1 map. The last thing that remains to be proved is that this is smooth. So this is a local study of the singularities of D2A in D3A, which we pull back and see. So proof smoothness is a typical result. So at the end, we have YA is a smooth. Smooth. We have the double cover, so D to A, and also we can compute the canonical class. That is trivial. So it has trivial canonical class. The difficulty now is to prove that it has a symplectic form. Don't degenerate. But of course we don't find the symplectic form. So now the step 2. Yes, we proved that there exists a smooth double cover, even we know what is the canonical class of this double cover. So we have more, but how to prove its hyperkernel? So the proof of hyperkerner is find special A. So I find special A such that this YA is birational to a Hilbert square of a K3 surface to some K Hilbert cube of a K3 surface. K of a K3 surface. Isn't so? This is more or less also the way how O'Grady proved his result. So there is a natural candidate for the A, which comes from O'Grady's construction, but it's not quite natural for our construction, but it works. So let me just, so I don't know how much time do I have left.
10 minutes.
10 minutes, okay. So let me just draw the picture. So we have this G36, and here we have two types of Lagrangians, but one of these types, so in O'Grady's construction, the natural Lagrangians to study were these fibers FA. These were just is what I call FA. These are Lagrangian spaces which intersect the Grassmannian G36 in the Grassmannian G25, because FA was like, so when V6, you can think of it as A times C plus some V5. So once we choose such a decomposition, then this FA is isomorphic to wedge 2 of V5. Yes, so FA is just the space of where beta was a 2 form, but all the 2 forms which have A inside, the 2 form gets killed, so we are left just with this V5. So this is in fact wedge 2 V5, and the intersection with the Grassmannian is exactly the Grassmannian in the wedge rectanulation of wedge 2 of V5. So for O'Grady, the special A that he considered was an A which meets some FA in a plane. So it means that S3 of A was non-empty, was a point. So consider such an A, that S3 is a point. We can have such an A for which our construction still gives a smooth YA. So the EPW, the double EPW sextic is singular in this case, but our EPW cube is still smooth. So that YA is still smooth. And then we associate to it a K3 surface, to this picture. So we still don't see the degeneracy locus. But so let me just extend the picture here. So we work on the dual space F a dual, which is just wedge 2 x V5 dual. Here we have the Grassmannian, the dual Grassmannian G25. We have this orthogonal P6 to this plane. So it's a P6 section of the Grassmannian G25. And to get a K3, we need a quadric, one more quadric. So the complete interaction of G25 with a P6 and a quadric is a K3 surface. So this quadric, we get it from the fact that A is Lagrangian. So it's some kind of trick for Lagrangians that they give us quadrics here in the this orthogonal to the intersection here. So we have a quadrant here in this P6. Go to this video quadrant. So quadrant to A, and here we have a K3 surface. Okay, so this gives us the K3 surface K. And so how to prove that K cube is birational to YL? So first we construct, we have this 2-to-1 map to D2A, which is branched in codimension 2. We will construct a 2-to-1 map here, also to D2A, which is also in codimension 2 defined and branched. And then this will be just outside the set of codimension 2. This will be universal covers, so they will have to be birational. So the missing part is a 2-to-1 map from K to D2. So the way to get it is to see that the space of quadrics containing K in this P6, there are Plücker quadrics coming from the Grassmannian, which are just parameterized by V5 dual, or in our case V5, because dual, V5 dual, sorry. And the additional quadric QA. Let's see. And now, so any 3 points on the K3 surface, we can associate the space of quadric vanishing on the plane spanned by these 3 points. It's a codimension 3 space in the space of all quadrics. So it's a codimension 3 space here, but this is dual. So we have a codimension 3 space in V6 dual, so we get a map from the Hilbert scheme to the Grassmannian G3 V6. And another technical part is to prove that the image of this map is in fact in D2A. So it's a 2-to-1 map. Is D2A. So this ends the proof. I hope I have still a few minutes, because I wanted to describe some recent work in progress. How to construct a fourfold out of this EPW cube construction. So the fourfold is work in progress. So what happens when A meets the Grassmannian G36? So far in our assumption of generality, A didn't meet the Grassmannian, but there is a divisor in the Lagrangian Grassmannian of such spaces which meet G36 in 1 point. Let's say it meets in 1 point. So if A meets the Grassmannian in 1 point, then we figured out that this singular, that this D2A is in fact singular in more, not only in D3A, but it's also singular in the intersection of D2A with a cone over P2 cross P2. So this cone comes from this intersection point. This intersection point is just U, and we have the tangent space to U intersect the Grassmannian in a cone over P2 cross P2. So in the Grassmannian here, we have this point of intersection A, and we have this cone of P2 cross P2, which is contained in the Grassmannian. And any tangent in any point of this cone passes through this vertex, because any tangent contains this line. So it passes through the vertex of the cone. So this cone is contained in D1A. This whole cone is contained in D1A. And it meets D2A in the hypersurface of degree 4. So if we denote this hypersurface with H4 just D to A intersected with the cone of a P2 plus P2, it's a fourfold. And this fourfold is singular in it has no name D, which is the intersection of the third locus with this cone. So this is a fourfold, and this is a surface. And if we can prove in the same way, so the double cover that is here is in fact a double restricts to a double cover of this fourfold in this surface. Yes. And so we can prove that the double cover of D2A in D3A, not D2A, but the intersection of H4 in D is a hypercolor fourfold. The double cover of H4 branched in D is a hypercolor fourfold. And this is a hypercolor fourfold of degree bogomol of degree 4.
So it is not the double.
No, it's not. It's kind of new one. But the point is that we got only a 19-dimensional family, because the A here, but intersecting the Grassmannian is a divisor. So the whole family gave us a 20-dimensional family of EPWQs. Here we have degenerate EPWQs, which are a 19-parameter family.
Picard number is 2.
The Picard number of the general one is 2, yes. In this family. Yes.
And
so, but there
with
is.
respect to the delta,
Once again?
what's the divisor of this degree is 4? So Picard number is 2, it's nothing.
Yes, 1 from the P2. Yes. So the point is that we know that when we have a polarization of degree 4, then there is this 20-dimensional space on which the general element is not a double cover. Yes, this one has a double cover. So this is like a hyperelliptic locus. We constructed a hyperelliptic locus in this moduli space of polarized of degree 4. So we don't know how to find the general element in the family, but we know how to find this hyperelliptic locus from this space. So it's a nice problem to find the general element of this family. And so one more thing that we know how to prove is that the elements here are not Hilbert squares of the K3 surface. So that's it. Thank you.
And what is the degree of the net from H4 to P2 plus P2?
It's 4 to 1. It's a quartic section, yes. So it's 8 to 1 in total. It's 2 to 1 cover, then a 4 to 1 now.
Is it enclosed by some group action?
So this 4 is it primitive? I mean, the corresponding relation is it primitive? Right. And do you know about the whole lattice? I mean, you have to mention the card to generate. So it's reasonable to ask what is the corresponding lattice. What is the square of the other generator and how they intersect?
This is not generator, it's sum of the generators.
Also generators, yes.
Yeah, but what is the
Intersection of 1 and 2.
So you have two-dimensional lattice. Do you know it?
Yes, I think we know it. 2, 2, yes. 0, 0, 2, 2. So it has two abelian integrations. That's what we said before. This gives an abelian integration. So on this cone here, we have these P3s, the pullbacks of P2s here are P3s. On these P3s, we have quartics, which are Kummer quartics. And the double cover is just this abelian integration, and there are two of them. So it's like, it has become number 2 with 2 abelian federations. And the sum of these 2 abelian, so the square of each is 0, and they intersect in 2.
And what is the branch divisor for this 41
More questions? Let's have this people again.
Announcement. So we have a lunch until 3, and unexpectedly we have a lunch here. So it's the usual canteen. Just we usually have a coffee break, and then we have a lunch. Here, 3 lunch. So follow the game.
So I can take a K3 session. Yes. Is it done with any extra
No, that's not.
That's not done.